So we're still looking at this problem, and we want to now get the solution that satisfies the initial conditions. So here's our general solution from last time. It has C1 and C2, and we want to find out what C1 and C2 will meet the initial conditions. Okay, so I copied over the general solution here, and my initial conditions are this: x of 0 equals 1 and y of 0 equals 0. So in other words, if I write x vector for both of them, that's 1, 0, right? 1, 0. So what value of C1 and C2 make this true? Make x of 0 be 1, 0. Well, I want 1, 0 to be, and then now let me just write x of 0. X of 0 is going to be C1, and then e to the 0 is 1, so just C1 times 1, 1, plus C2 times e to the 0 is 1, so 2, 3. This is pretty much why we like initial conditions to start at t equals 0. It makes things easy, but not that things would be much harder if it weren't times 0, but it is just very nice that e to the 0 is 1. Okay, so we're here, and we're trying to find what C1 and C2 make this true. Okay, you've probably been here a million times, right? This is like trying to solve this matrix vector equation. So what matrix of coefficients, what vector of coefficients, C1, C2, will have the property that when I apply this matrix to it, I get 1, 0. Okay, and you can solve the linear system in any way that you want, but I'm going to just point out that if you don't mind inverting this matrix, there are a bunch of ways you can do it. You can do it in Mathematica. You can follow some formula for inverting a matrix. Whatever you do, if you just find some automatic technique for inverting this matrix, then it can save you some effort instead of having to go through and solve linear equations. So it can save you some effort, and it can get you a quick general result, actually. If I want to just handle any pair of initial conditions, not just 1, 0, but let's say x naught, y naught. Could have been anything, x naught, y naught. Then this is the problem I'm interested in solving. What is the relationship between C1, C2, x naught, and y naught? So can I solve for C1 and C2? Yes. C1 and C2 are whatever is the inverse of that matrix. That matrix inverse applied to x naught, y naught. So then I have to go find the inverse. Okay. And there it is. That's nice. No fractions. 3, negative 2, negative 1, 1. I typed that incorrectly. Yep. Okay, so there's your C1. C1 is, times this vector of initial conditions. So C1 is 3x naught minus 2y naught, and C2 is negative x naught plus y naught. So here's a much more useful way of actually writing the general solution. So let me go back, grab this general solution that I had. Let me copy that. It pastes it in the wrong place. Okay. There. So now I have a much more useful way of putting in the unknown parameters. Rather than putting C1 and C2, how about I put in what C1 and C2 are in terms of the parameters x naught and y naught. So let me make space for those. So I erased C2 here, and I erased C1, and instead I'm going to put, what is C1? It's 3x naught minus 2y naught. And C2 is minus x naught plus y naught. Let's write y naught minus x naught. So that's even better than what was being asked in the homework problem. The homework problem just wanted one initial condition, but here we've solved all possible initial value problems for this particular differential equation. So insert initial conditions here for x naught and y naught, and get out the solution that satisfies those initial conditions. So let's see, if I want out of this the specific situation where, like it says here, x naught is 1 and y naught is 0, then I would get 3, you're putting 1 here, I think I would get this. I don't know why I wrote a 3 there. I think I would just get this. If x naught is 1 and y naught is 0. So then, remember, this is vector x of t. So it's this x of t, y of t package is this. So if you just write out what are x of t and y of t, that's what you would be putting into these blanks. And I just checked it to make sure that this actually works. And okay, so a couple of things we wanted to do. Yeah, a few things left in this lecture. One is to talk about the classification for critical points, and another is to actually now go and watch that solution play out, watch the animation. So let me just go here, put in, I think C1 was 3 and C2 is -3. So here's where I was choosing them. 3. Sorry, why do I keep saying that? It's -1 there. And -1. And let me make sure that starts in the right place. Yep, it starts at 1, 0. You see that dot starting at 1, 0. And then you can see what it does. It actually looks like it's traveling in a straight line, but I promise it's not. Maybe if we zoom in a little bit, that'll be more clear. Nope, I zoomed in, slowed down, the animation still looks like it's traveling in a straight line, but I really promise it's not. It's just a very low curvature. That's because we're in this region. How about we try something in this region? I think that'll look more interesting. You can see these tend to have high curvature. So let's see, I want something starting not at 1, 1, but above, but not too far above, so not all the way at 1, 3 halves. So between a vertical coordinate of 1 and a vertical coordinate of 3 halves, somewhere in the middle. How about 1 over and 5/4 up? So then I'm putting in 1 for x naught and 5/4 for y naught. Actually, I'm just going to type in this for C1 and C2 and fix them in this line. So inverse of this matrix times, and then I want 1 over and 5/4 up to be my initial condition. That seems to work. I do think I'm starting 1 over and 5/4 up, but now it's playing too slowly. So play out to 1 second. Now you can definitely see that it's a curved trajectory. Let's also plot the actual trajectory that's being followed. So that's parametric plot. Let's do the same time range. There it is. Okay, for some reason that looked really weird, but here it is. So you can see the trajectory is kind of curved. And I wonder what other, maybe I can find a nicer one here. Okay, I found a nice one. So if I put in 2, 3 as my initial conditions, then I just travel down this blue line down towards the origin, and that's not so interesting. But if I start just a little bit under the blue line, that's actually a good way of getting one of these cool looking ones. So instead of 3, 2.95 seemed to be a good one. You can see that's one of these red curves here. So all of that gaining control over the initial conditions came from knowing how to get C1 and C2 in terms of initial conditions. So apply the inverse of this matrix to this. Now finally, about the kind of critical point we were looking at here. So we've got So 0 is a critical point, right? It's the critical point. Any solution that starts at 0 stays there. I guess the first question we can have is it a stable or an unstable critical point? And it looks like this is actually a mixed situation, right? Where if you start perfectly along the blue somewhere, then you would just go down towards the origin, right? So if you were to deviate away from the origin, like say this is your system determined by two numbers, the state is determined by two numbers at any given time, x and y. If your system is at 0, 0, then it stays there forever, but if you blow on it and perturb it slightly, if you move it along the blue line, so if you perturb it just perfectly so it's along the blue line, it comes back towards the origin, right? Either way. If you perturb it here, then also it'll come back to the origin. But any other place you move it to, like here or on the green line, it'll explode out away. So in this mixed situation, you would say it's unstable. So the origin there is an unstable critical point. But we also have a more fine-grained classification. So there are several types of unstable critical points. This particular one with this kind of picture, where it's mixed and you actually have one line along which you have stability, one line of instability. So one stable eigensolution, one unstable eigensolution. In this mixed situation, you would say this is a saddle point. So that's, I guess I'm giving you the answer to one problem, is this one is a saddle point. And the way to know that this is what you end up with, before you draw any pictures, so this is the typical picture of a saddle point, but before you draw any pictures, you know it's going to be a saddle point just from the eigenvalues, that one eigenvalue is positive and the other is negative. So all of these other critical point types are going to be related to other situations with eigenvalues. So for example, if both are positive, or if both are negative, or if they're complex, then depending on the sign of the real part, or maybe what's going on with the imaginary part, that might tell you some things about the type of critical point that the origin is. Or you could also have repeated eigenvalues. And then that's a whole other thing. Okay, so I think I've given you everything you need for the homework, except that I haven't discussed the other types of critical points that show up in problems 8 and 9. So this lecture kind of ran long, so let me try to quickly just discuss those without going through detailed calculations in the next video.